if I'm looking for a root of the function, or if I'm looking for all the roots of the function. Two different questions, okay? If I'm looking for a root of the function, or if I'm looking for all the roots of the function. I said roots. So by that we mean you are looking for all the values of x satisfying the condition that the value of the function at those numbers is equal to 0. Now, for instance, for the function on the screen, f of x, anybody want to tell me the two roots of the function? The function has two roots. The function has two roots. So do you want to tell me what are the two roots of the function, please? I mean, what values of x will make the values of the function 0? These are the two roots. To solve for two roots, so all we need is in this, 1 and -1 are right. To solve for the roots, all you need is to let the function be 0, and then you have something like x squared minus 1 is equal to 0, right? And then for this one, x squared is equal to 1. So you are looking for two values of x, having the condition that the square of the values is equal to 1. So you see x value is equal to plus or minus 1, right? So the function has two roots. That's a simple one. So, but not for all the functions it's simple to find the roots. In many cases, you have to approximate the roots. Okay. When the function is more complicated, Newton's method will give you a very efficient way to approximate the roots. So that's the whole idea. Okay, now let's take a look at the video. Okay, Newton's method. We now talk about the Newton's method. The Newton's method is used to approximate roots of functions. Let's recall a special case of the intermediate value theorem. The condition is that the function is continuous on some closed interval from a to b. If the values of the function at a and b have different signs, then the function must have a root between a and b. Okay, this conclusion is called IVT, the intermediate value theorem. I'm going to write it on the PowerPoint. It's called IVT for intermediate value theorem. Okay. We only need a special case of the conclusion. We only need a very special case of the IVT. Okay. You look at the statement of IVT. Okay. Two conditions: the function is continuous on the closed interval, and the other condition is the function has different signs at a and b. I mean, the value of the function at a and the value of the function at b have different signs. Under the two conditions, you can conclude the function has at least one root on the interval from a to b. Okay. How about I will use a question, so we're going to see later to show you the meaning. On the wrong handout. Sorry. The question is designed to show you the meaning of IVT. What are the conditions of IVT and how to use the IVT? Now, for instance, for the question on the screen, the function is x squared minus 5. If I want you to show the function has a root in between 1 and 5, now the solution to that. In general, if I want you to show something, you write proof. I know you hate proofs, but so this one is simple. Okay. For this one, all we need is to verify two conditions. So the first condition is the function is continuous on the interval from 1 to 5. The function, so which is x squared minus 5. We mentioned before, this function can be written using one formula, right? By that we mean this function is elementary. More precisely, elementary function can be constructed from all the building blocks we mentioned before by performing addition, subtraction, multiplication, and division. If you want to see that way, this function is the subtraction of two functions in the building blocks. X squared is a power function, right? That's a function in the building blocks. And 5 is a constant function, right? Or the bottom line, you just remember if a function can be written using one formula, then the function is elementary. An elementary function is continuous at any number on the domain, right? We mentioned the conclusion before. Recall the continuity. So you just mentioned the function is continuous, right? The function is continuous at any number on the domain. You see the domain is the set of all the real numbers. It's continuous on the set of all the real numbers. So can we just use the interval notation to indicate the set of all the real numbers? Okay. And then you say something like, in particular, to use IVT, the continuity condition, it means the function is continuous on the closed interval from A to B. You see the conditions here, right? The function is continuous on the closed interval from A to B. I will show you what's going on in this particular case. Okay, the function is continuous at any number, at any real number. In particular, the function is continuous on the interval from 1 to 5. So do you see the key numbers 1 to 5? Okay, mention the continuity condition. Okay. Moreover, the other condition you have to check is the value of the function at two endpoints at 1 and 5 have different signs. One value is positive, the other number is negative. It doesn't matter which one is positive, which one is negative. Okay. Moreover, we evaluate the function at 1 first. Okay. The value of the function at 1, it's easy to see that the function is x squared minus 5. The value of the function at 1 is 1 squared minus 5, right? 1 squared minus 5, so which is negative 4, right? 1 minus 5 is negative 4. And the value of the function at 5, you evaluate that. The value of the function at 5. 5 squared minus 5. So do you have 20? You have 20. Okay. 5 squared is 25 minus 5. You have 20. The second condition is that the value of the function at 1 and the value of the function at 5 have two different signs. One value is negative, the other value is positive. So you see that condition is satisfied, right? So you say something like the value of the function at 1 and the value of the function at 5 have different signs. You see the two conditions of IVT are satisfied. And that. So do you see you have two conditions? One condition is the function is continuous. The other condition is the value of the function at A and the value of the function at B. In that particular case, the value of the function at 1 and the value of the function at 5 have different signs. The two conditions are satisfied. If the two conditions are satisfied, then you can use the conclusion. The conclusion is that the function must have a root on the open interval. Okay. So maybe thus, I do not want to use so all the time. Okay. Thus, the function has a root, or at least one root, or okay, has a root between 1 and 5. Actually, for this one, you can imagine you know the root. The root is kind of square root of 5. But I'm going to use a simple question to illustrate the Newton's method. Okay. Actually, the question is equivalent to we're trying to approximate square root of 5. You're going to see it. Okay. Any questions about this? So verify the two conditions. Actually, I want to make a little bit more comments. Okay. Actually, the thing is true in general. So now let's try to see the geometric meaning. Okay. So now let's say if you have the graph of the function, so we kind of know the graph. Okay. But now I want to talk about something in general. Okay. So now let's say x value of 1 is there. I was trying to draw x value of 1 is here. Okay. And then x value of 5 is here. Okay. You know the value of the function at 1 is negative. The coordinate system, the x-axis and the y-axis may not be proportional. Okay, I may not talk about the question. So this question, it's kind of the value of the function at 1 is negative. So now let's say the value of the function at 1 is negative. So this is a point on the graph, right? And the value of the function at 5 is positive. Now let's say positive 20 or positive any other number. So the value of the function at 5 is positive. You look at the screen, or you look at the mouse cursor. The value of the function at 5 is positive. It means this point, the point on the graph of the function when x value is 5, is above the horizontal axis. So that makes sense. The value of the function at 1 is negative. It means the point determined by x value of 1 is below the horizontal axis, right? And then the function is continuous, right? We have that condition. So the function, the graph of the function, it has to be something like that. What is the meaning of the conclusion? The conclusion, it means the function has a root in between 1 and 5. So maybe my sketch is not too perfect. So can I try again? The sketch, the graph, so it could be something like this, right? In any case, you see the curve and the horizontal line, they must have a point of intersection. Okay, I used to say this way actually. So now let's say if this point is on Peace River South, so which is in Dawson Creek, and the value of the function at 5 determines a point on Peace River North. Now let's say to travel from Dawson Creek to Fort St. John, you have to pass the Peace River, right? That's the point of intersection. So do you know what I mean? This point of intersection has the property that the value of the function at this point is equal to 0. Look at the mouse cursor. That's the point of intersection, right? Which means the value of the function at this point is equal to 0. That is the root, right? But in general, IVT does not give you the value of the root. IVT just tell you there must be a root in between 1 and 5. You travel from Dawson Creek to Fort St. John. You know you have to cross the river, right? You don't know where to cross. IVT does not tell you where to cross the river. So that's the geometric meaning of IVT. It doesn't matter if you do not fully understand that, as long as you know how to use IVT, it's okay. But I think geometrically you can see IVT is true. So that's my point. I told you the meaning of IVT already, right? Now let's keep on going. Any questions so far? We have learned how to approximate roots using IVT, the intermediate value theorem. Now we are looking at a more sophisticated and effective way called Newton's method. We now assume the function is differential. The questions on the screen are designed to motivate the Newton's method. To use the Newton's method, we need an initial approximation, say x0. In question 1, we need to get the linearization of the function. A little bit more comments on this. Okay. Initial estimation. Now let's say if now for instance, for the question on the screen, later on we are going to use the Newton's method to approximate the root. Okay. The initial estimation, you do not know where the root is. In most cases, as a rule of thumb, use the midpoint as initial estimation. By that we mean if the one endpoint is 1, the left endpoint is 1. If the right endpoint is 5, the midpoint is a 3. I think the midpoint is 3, right? Use the midpoint as initial estimation. I want to repeat, in many cases, use the midpoint of the interval as the initial estimation, as the value of x0. You are going to see the meaning in more details very shortly. At x0, the linearization is denoted by L of x. It equals the value of the function at x0 plus the derivative of the function at x0 times, in brackets, x minus x0 is a linear function. So we just learned that, right? So linearization of the function at x0. You just replace a with x0. Now, the idea of the Newton's method is to use the root of the linearization of the function to approximate the root of the given function f of x. Geometrically, okay, you look at the graph. The graph is on the handout. Okay, I told you to download the handout. You see x0 is the initial estimation of the root. The actual root is point C. So do you see the actual root is the red dot, the red point, right? The actual root is C. Why did I use C to denote the root? I forgot. Now let's say x0 is initial estimation, okay? And then we can get linearization of the function at x0. The graph of the linear function is the tangent line to the curve. Now let's say the curve is the graph of the function f. Okay. The root of the linear function in general is simple to compute. We're going to compute that later. But the root of the linear function is x1. Now the idea is to use x1 to approximate c. C is the actual root of the function. x1 is the root of the linear function. Okay. The first step we do is to use x1, the root of the linear function, to approximate c, the root of the given function f. So that's the idea. Okay, now let's keep on watching the video. Yeah, this is the video. Graph of the linearization is the tangent line to the graph of the function at this point. This point has x coordinate of x0. Now on the sketch, the root of the given function is c. The root of the linearization is x1. The idea is to use x1 to approximate c. A little bit more comments on this. Actually, the root of the linear function x1 is actually using another term. Is actually the x-intercept of the tangent line. I'm going to say it again. Try to understand me, okay? X1 is actually the x-intercept of the tangent line. now the problem is how to get x-intercept, or the root of the linear function. To get x-intercept, you set y value to be 0, and then you solve for x. That's how you get the intercept, x-intercept. So that makes sense? So because this point is on the horizontal line, any point on the horizontal line has y coordinate of 0. So for the linear function, you set y value to be 0, and then you solve for x. That's how you get the x-intercept. You're going to see the idea very shortly. Okay. In question 2, we are looking for the root of the linear function L of x. By that we mean we are looking for a value of x at which the function value is equal to 0. So you set y value to be 0, and then you solve for x. So I told you that that's how you get the x-intercept, right? So we need to solve the equation L of x equals 0 for x. The same thing as y be 0. You let y be 0, right? X. By that we mean f of x0 plus the derivative of the function at x0 times, in brackets, x minus x0 equals 0. The equation is equivalent to f of x0 plus the derivative of the function at x0. You multiply out. By that we mean you distribute the derivative of the function at 0 into these two terms, times x minus the derivative of the function at x0 times x0 equals 0. And then we are going to solve the equation for x. That will give you the x-intercept. To solve for x, we need to isolate x. So we move these terms to the right-hand side of the equation. We have the derivative of the function at x0 times x equals, on the right-hand side, we have the derivative of the function at x0 times x0, then minus f of x0. We now divide two sides of the equation by the derivative of the function at x0. We have x equals x0 minus a quotient. On the numerator you have the value of the function at x0. On the denominator you have the derivative of the function at x0. Because we use x1 to denote the root of L of x, this is x1. So maybe try to follow this. I think it's not too hard to follow. So just some notations for the general function could be a little bit weird to some of you guys. It's essentially x0, the value of the function at x0 is a number, is a constant. The derivative of the function at x0 is a constant. x0 is a constant. The only unknown is x. You solve the equation for x. It's kind of that. Okay. Now actually this is the formula you're going to use. I'm going to make more comments on that very shortly. But I'm trying to say, what I'm trying to comment now is if you understand the argument in here, it's better. If it's hard for you to follow, it doesn't matter. The bottom line is to know the formula, and how to use the formula. Okay, now I'm going to make some comments on this. Okay. Now let's recall x0 is the initial estimate, and then I will show you very shortly. Using that formula, you can get x1. In general, x1 is closer to the actual root than x0. I'm trying to say x1 is in general a better approximation. I will show you the meaning. So maybe now let's look at the thing graphically. I have too many things open right now. It's probably where is it? Okay, now you look at the graph in here. Okay, x0 is initial estimate. Okay, and then the root of the linear function is x1. I mean the root of linearization is x1. We have seen how to write x1 in terms of f and so on. Okay, we have a formula to compute x1. I mean, okay. So do you see x1 is actually closer to the actual root, the red point, the x0? And then what you do next? After getting x1, you use x1 as an estimate. You do the same thing. Okay, and then you get linearization of the function of the given function f at x1. So which is the green line. Do you see the green line? The green line is actually the tangent line to the graph of the function when x value is x1. And then you keep on doing. After getting x1, you do the same thing. You can use the kind of the same formula to compute x2. Actually, x2 is the x-intercept of the green line of linearization of the function at x1. And then you just keep on going, and then you can have x3. x3 is better than x2. Okay, and then you can have x4 and so on. Okay, so we'll go back to this. Okay, very shortly we're going to use the particular questions to show the meaning. But if you look at the screen, the PDF, again x0 is initial estimate. You need this number. Okay, after getting x0, you can use the formula to compute x1. In general, x1 is closer than the actual root. After getting x1, you can kind of using the same formula to compute x2. x2 is an even better approximation. And then after getting x2, you can get x3. It's even better. And you keep on going until the required accuracy is reached. Again, the Newton's method is essentially one formula. Okay, I believe as long as you can remember one formula, and then all the formulas are easy. Okay, now I'm ready to show you a particular question. Probably we can show you the solution to two questions. What question is this? I think this is sorry, I have too many things open. This is question 1 in this part. I don't know so which part. So example part, right? So we'll do this question first. Okay. I think we have seen question A. How to do question A, right? To do question A, you use IVT. You verify two conditions. The function is continuous on the closed interval from 1 to 5, and then the value of the function at 1 and at 5 have two different signs. So first of all, you convince yourself, or convince me, there's a root in between 1 and 5. Now we are going to use the Newton's method to approximate the root. Okay. Initial estimate, I told you before, in general we use the midpoint as initial estimate. The midpoint of 1 and 5, I said it's 3. How do you compute 3? 1 plus 5, so divided by 2, you have the midpoint. Okay. 1 plus 5 is 6, so divided by 2 is 3, right? So you use that as the initial estimate. So we'll keep on doing to do question number B. Okay. I'm going to copy the entire question to next slide. It's too big. Now we're going to do question B, okay? Again, to use the Newton's method, you need to choose a initial estimate. In most cases, we use the midpoint of the interval from 1 to 5 as the midpoint as initial estimate. Okay, so maybe let x0 be 3 equals 3 be initial estimate, the initial estimate. Initial estimate. Okay. Now, so get your calculator, please. Get your calculator. So we are going to. You need to use a calculator or some computer programs to do a question like this. Okay. We use x0 value of 3 to be initial estimate. So before we compute x1, yeah, probably we need to get the derivative first. Okay. Now let's copy the function first. The function is x squared minus 5, right? The derivative of the function is simple to compute. It's just 2x, right? It's just 2x. After getting the derivative, we are ready to have a formula for computing x1. So copy the formula first. Okay. You look at the handout. x1 is computed. I'm talking about this one. Okay. x1 is computed using x0 minus the value of the function at x0 divided by the derivative of the function at x0. I just copy the formula to here. Again, you use x0 value of 3 to compute this. So x1 is computed using x0, which is 3, right? And then minus the value of the function at x0 on numerator, okay? So which is 3 squared minus 5. And then on denominator, you have the derivative of the function at x0, which is the value of the derivative at 3. Okay. I think we can just plug in the number. It's 2 times 3, right? The derivative is 2x. If you replace x with 3, the derivative of the function at 3 is equal to 6. I prefer to write that in the form as 2 times 3. So do you see what's going on now? Again, x0 value is 3. Wherever you see x0, you replace x0 with 3. Okay. And then on the numerator, you have the value of the function at 3. The function f of x is here. The value of the function at 3 is given by 3 squared minus 5, right? And then on denominator, you have 2 times 3, x value 3. Okay, so please, so get your calculator, please. So can anybody tell me this value? This value, please. Keep as many decimal places as possible. So probably I'm going to do this on the R program. The numerator is I'm trying to say the numerator is the value of the function at x. On the numerator, you have x squared minus 5. On denominator, you have the derivative of the function, so which is 2x, right? 2 times x. Of course, you cannot compute yet. I need to set x value to be initial estimate. Initial estimate, x value is, I think we're trying to use 3. Okay. And then you use the formula to compute. I think I did something wrong. On denominator, there should be some brackets in it. So do you see you have this number? So 0.96 and then 7. Now plug all the numbers into calculator, please. So do I get this number right? Okay, for this number, I will copy this number onto the PowerPoint. Okay. Again, for this value, try to keep as many decimal places as possible. Okay. 0.96. Probably I did something wrong. Sorry, I think I did something wrong. So most likely I did something wrong. Anybody want to tell me the right number, please? I think I did something wrong in the R program. Sorry. It should be x minus this. 2.93. Oh, thank you. So thank you. Okay. This value is, sorry, I forgot to subtract the number from 3. Again, when doing this, try to keep as many decimal places as possible. Okay. Try to keep as many decimal places as possible, or better, use the store function on your calculator. I think for TI calculators, on most calculators you have a store function. So try to store the values. Okay. I will show the meaning using a little video. I made a little video showing you how to press the buttons. I will show that later. Okay. But the point is, after getting x0, and then you can use x0 and the formula to compute x1. Okay. Now I will show you some more details how to use x1 to get x2. It's actually the same formula. Now let's recall, x2 is computed. You just look at the formula for computing x1 from x0. x2 is computed using, wherever you see x1, you replace 1 with 2, and then you replace, wherever you see x0, you replace x0 with x1. So the formula to get x2 from x1 is the following. It's x1 minus, on numerator you have the value of the function at x1, right? And then on denominator you have the derivative of the function at x1. Okay. So this time I'm going to plug in the numbers, showing you the meaning. You see x1 value is 2.3323 something. So how about, so temporarily we just keep 4 decimal places. Okay. We just keep 4 decimal places. When you actually do the question, I want you to either keep many decimal places or use the store function on your calculator. It's approximated by that number. Okay. And then the value of the function at x1 is 2.3333, right? And then minus, on numerator, I mean x1 is 2.3333. Okay, we got the value of the function at x1, and then on numerator you compute the value of the function at x1, so which is 2.3333 squared. You look at the mouse cursor. The value of the function at x1 is computed using that formula. You plug x1 value of 2.3333 into that function. Okay. This number squared minus 1, and then on denominator you have the derivative of the function at x1, so which is 2 times 2.3333. Using that formula we can get the second, we can get the value of x2, which is called the second iteration. Anybody want to try this number to get the next number? don't know you're computing or not, but if you actually compute, you have this value. You have this value. Actually, for this class, the reason I use videos is because I hate calculators. I'm not good at calculators actually. Okay, but I can use videos to make that up to show the meaning. So can I just keep on playing the video now to show you what's going on? Item number 3 is basically the statement of the Newton's method. The meaning is that if we know the initial estimation x0, then we can use the formula to get the next approximation x1. After getting, you have seen the point, right? x1, we can use the same formula to get a better approximation x2. And by the way, it's not always better, but in most cases, it's indeed better. If the function is nice enough in some sense, getting x2, we can get an even better approximation using the same formula. Eventually, we can get approximation at a required accuracy. At this point, I want to make a comment. The Newton's method may not be working for all functions, and the sequence in question 3 may not approach the actual value of the root very fast. For item number 4 on the screen, we are going to use particular questions to illustrate the meaning. I will show the meaning very shortly. We now work on the question. To show the function has a root between two numbers, we use the intermediate value theorem. Verify the two conditions. The function is continuous on the closed interval, and the values of the function and the two numbers have different signs. One is negative, the other is positive. Next, choose an initial estimation. Use a nice number on the interval, like the midpoint, as an initial estimation. Then use the Newton's method formula to calculate one approximation after another, until the required accuracy is reached. I wrote some R code for the I did that in the video. I'm going to make more comments. The detailed calculations. This can also be done with a calculator. Now you look at the first line, okay? The first line is on your TI calculators. For most calculators, you have a store function, right? The first line, it means if you do it on calculator, you store 3 in the variable x. You store 3 in x. So wherever you see x, x is going to have the value of 3. Okay. This line means the initial approximation is stored in the variable x. This is x0. And then in the next line, you look at the next line. On the right hand side, you look at the mouse cursor, okay? You look at the mouse cursor. This part on the numerator, you have the given function. Actually, it's the formula for the Newton's method. If you have x value of 3, this line is essentially computing 3 minus the value of the function at 3 divided by the value of the derivative at 3. Is the Newton's method formula, right? And then this number after calculate is going to be stored in x again. We have seen this number already. It's 2.333 something. It's essentially how to use x0 to compute x1. This is the Newton's method formula. Use x0 and the Newton's method formula to calculate the value of the next approximation and store the value in x. This is x1. We have seen x1, right? you have told me the answer to x1 already. Use x1 and then we use x1 to compute x2 using the same formula. x1 value is 2.3333 something, right? It's stored in x. And then this line is actually the Newton's method formula. After applying the Newton's method, when x value is x1, and then you store the value to x again, the next number is going to be x2. The Newton's method formula to approximate the value of the next approximation and store the value in x. This is x2. We keep on going until we see the first 4 decimal places stop changing from one iteration to the next. I think in the question I want you to round the answer to 3 decimal places. Again, we are trying to approximate the root of x squared minus 5. You look at the question on the handout. You see after, okay, that's x0, that's x1, that's x2, that's x3, that's x4. From x3 to x4, you see the first 4 decimal places are not changing anymore. And then you can get the answer. If I want you to round the answer to 3 decimal places, the answer is going to be 2.236. It's because the first 4 decimal places are not changing anymore. So did I make it clear? We're ready to give the answer to the question. You see the answer is 2.236. So because the first 4 decimal places are not changing anymore. We're ready to give the answer to the question. You see it's 2.236, right? So any questions about this? So of course, after the class, you need to try some questions. So later on, I'm going to give you some more hints. Okay. But in the video, I showed you one other question. So how about we take a break after I show you one other question? Okay. We now work on the question. To show the function has a root between 2 numbers, we use the intermediate value theorem. Verify the 2 conditions. The function is continuous on the closed interval, and the values of the function and the 2 numbers have different signs. So this part is simple. I did not go over that in very detail, but evaluate the function at 0. Cos of 0 is 1. And then you plug 0 into the function, you have the value of the function at 0 is negative 1, which is negative. And then the value of the function at pi, cos of 2 pi is equal to 1 as well. So the answer you are going to get is pi squared minus 1. Okay. You know pi is 3.14 something. The whole thing is positive. Actually, we're trying to verify the 2 conditions of IVT. The first condition is that the function is continuous on the interval from 0 to pi. The second condition is the value of the function at 0 is negative. The other one is positive. So the values of the function at 2 endpoints have 2 different signs, right? So the function has at least 1 root in between 0 and pi. The idea is, the first thing we do is to do what? To confirm there must be a root in between the 2 numbers. In this particular case, 0 and pi. And then using the Newton's method, we approximate the root. And by the way, for question 2, the actual root is very hard to compute, or next to impossible. But we can use the Newton's method to approximate the root. So pretty quickly. One is negative, the other is positive. Next, choose an initial estimation. Use the interval concerning in the question is the interval from 0 to pi. You'll see the midpoint is half pi. That's why I was trying to use half pi as initial estimate. Okay. nice number on the interval, like the midpoint, as a initial estimation. Actually, in step B, it's probably better if you compute the derivative first. It's simple, right? Using the chain rule. After doing that, so you can figure out the denominators. Okay. Now let's look at some details. X1 computed from x0. You know the formula, right? X0 is half pi. Is that half pi? And then for the quotient part, the value of the function at half pi, you just plug half pi into the given function. The given function is here, x squared minus cos of 2x. You have x squared minus cos of 2x. X value is half pi. And then on denominator, you just plug half pi into the derivative of the function. Okay. And using your calculator, you can get a decimal value. Okay. Again, if you do not want to use the store function, try to keep as many decimal places as possible. Okay. Then use the Newton's method formula to calculate one approximation after another until the required accuracy is reached. I wrote some R code for the detailed calculations. This can also be done with a calculator. This line means the initial approximation is stored in the variable x. This is x0. This is the Newton's method formula. Use x0 and the Newton's method formula to calculate the value of the next approximation and store the value in x. This is x1. Use x1 and the Newton's method formula to approximate the value of the next approximation and store the value in x. This is x2. We keep on going until we see the first 4 decimal places. Again, in the question, I think I asked you to round the answer to 3 decimal places. Okay, that's x0, x1, x2, x3, x4, x5. After you get x4 and x5, you see the first 4 decimal places are not changing anymore. Even if you compute more, the first 4 decimal places are not changing anymore. The most likely the first 3 decimal places are right. That's why the answer is going to be 0.601. Why do I have 1? When you see 7 on the 4th decimal places, and then you round up. So do you know what I mean? When you see a number, the digit at the 4th decimal place is a number 5 or bigger, then you round up. So the final answer rounding to 3 decimal places is 0.601. Stop changing from one iteration to the next. We're ready to give the answer to the question. The next question is designed to show that the Newton's method does not always work. So don't worry about this. This is a weird function. I told you before, if the function is nice enough, in most cases the Newton's method will work. What you learned today is in the future, when you do some other courses in other sciences, if you see an equation that is very hard to solve, think about the Newton's method. The Newton's method can give you a very efficient way to approximate the root. Okay. I made another video long time ago showing you how to press the buttons. By the way, I'm not good at calculators. I tried a little bit hard to make the video, but I hope it will show you something. The following question is going to be on the assignment. The next video is trying to show you how to press the buttons to approximate the root of that function in between 4 and 6. Okay. Of course, the first thing you do is to show the function has at least one root in between 4 and 6. Verify the two conditions. The function is continuous on the interval from 4 and 6. The second condition is evaluate the function at 4, evaluate the function at 6, and convince yourself the value of the function at 4 and the value of the function at 6 have two different signs. And then initial estimate you want to choose is probably 5. 5 is a number, the midpoint of the interval from 4 to 6. Again, we agree on to use the initial estimate of 5. And then I'm going to play a video showing you how to press buttons on your TI calculator. Okay. And by the way, the TI-84 something is free for computer use. It's probably free for Android phone if you want to download an app. I forgot how. I did that a long time ago. Okay. You ready? Again, the following video is showing you how to press the buttons to use the formula for the Newton's method to solve the question on the screen. In particular, the question on screen, the second part. Okay, this is the question that is going to be on the next assignment. Ready?
1. Store an initial estimate, say 5, in a variable, say x. Note that the variable stores x0.
You see, you have a store button here, right? That button is store. So press that button, and then you store the value of 5 in some variable a or x or whatever. So probably I was trying to use x.
Two. Enter the basic formula for Newton's method on your calculator.
You see, the Newton's formula is actually x0 minus the value of the function at x0, and then on denominator you have the derivative of the function at x0.
We have the first iteration through the formula for x1. Store this value in a variable, say x. Note that the variable stores x1.
The number calculated is x1. This is the value of x1. Remember, x0 is 5. That's how you x0 to compute x1 on your calculator. You do not write this number down. Instead, you store this number back again into x on your calculator. That's the thing I'm going to do the next. The answer is 4.464 something, right? You store the answer to x again. Now x is now the value of x1 is stored in x again. So do you know what I mean? And then you use the whatever button to recover the formula again.
3. Enter the basic formula for Newton's method on your calculator.
You know how to recover the formula without typing again, right? You can use the up-down button.
Calculator, we have the second iteration through the formula for x2.
So yeah, so that's x2.
Store this value in a variable, say x. Note that the variable stores x2. 4. Enter the basic formula for Newton's method on your calculator. We have the third iteration through the formula for x3. Store this value in a variable, say x. Note that the variable stores x3. 5. Enter the basic formula for Newton's method on your calculator. We have the fourth iteration through the formula for x4. Store this value in a variable, say x. Note that the variable stores x4.
You just keep on going. If I want you to round the answer to 3 decimal places, you just keep on going until you see the first 4 decimal places after the decimal point are not changing anymore, and then you can have approximation to 3 decimal places. Any questions?
At this point, we are accurate to 3 decimal places, 4.529. 1.
Again, on the assignment, that's going to be one of the questions regarding the Newton's method. There will be one other question. Okay, I want you to try independently. Okay. For this question, I showed you how to press the button on the video already. So probably this video is recorded already, so that you have this thing. On the new video, I'm going to pause this one. Okay. Any questions? Newton's method.